If the universe is infinite and filled with stars, the night sky should glow like a brilliant sheet of light, because wherever we look, our line of sight ought to land on the surface of a star. Instead, what we see is a wall of darkness stretching out behind the twinkling light of scattered stars, a boundary that appears to mark the edge of the universe. In reality, however, this is not the limit of the universe itself, but rather the limit of our ability to observe it. It represents the farthest region of the cosmos that we have been able to see. This is known as the observable universe. This boundary extends 46.5 billion light-years in every direction around us, forming a spherical shape. At the center of this sphere lie we, you and I, along with every object in the universe that we have discovered so far or will discover in the future. A light-year is defined as the distance light travels in 1 year, with light moving at a speed of approximately 300,000 kilometers per second. This is a fundamental law of physics. All light in the universe travels at the same speed, and no object can travel faster than the speed of light. We now know that the boundary separating our observable universe from the rest of the universe is not a wall of darkness, but a wall of light. However, this is not the kind of light we are familiar with. It is the primordial light that originated from the Big Bang. Although our eyes cannot see it, it is certainly there. To understand this, it helps to view light in the form of waves. Imagine throwing a stone into a calm pond. Small ripples form on the surface. Initially, these ripples are close together, moving outward in tight circles. But as they travel further from the center, their height diminishes and the distance between them increases. By the time the waves reach the edge of the pond, it might appear as though the impact of the stone has had no effect there at all. Yet, with a highly sensitive instrument, one could detect extremely faint waves reaching the very edge of the pond. That is why we have built highly sensitive instruments like the James Webb Telescope, which can peer much deeper into the light spectrum than is possible with the human eye. When light waves stretch beyond a certain point or age past a certain limit, they shift outside the range of our visible spectrum. We call these light waves infrared. You may have heard that night vision goggles can detect infrared light in the dark, though only over very short distances. If you were to look into space using night vision goggles, you wouldn't see the infrared light originating from the Big Bang. However, the James Webb Telescope can detect infrared light from much greater depths. Consequently, in regions of space that appear completely empty and black to us, James Webb can reveal every star, galaxy, or cluster that exists or ever existed there. Yet even when observing with the James Webb Telescope, that wall of darkness at the edge of our universe remains visible. That wall of darkness appears even behind the images of the most distant galaxies captured by the telescope. So, if even the James Webb Telescope cannot see past that wall of light, how do we know it is there? To understand this, we need to delve deeper into the nature of light. Beyond the range of human vision, light waves take on forms that are difficult to even visualize or imagine. We call these microwaves. We are surrounded by microwaves on all sides. The light emitted after the Big Bang was initially extremely hot and brilliant. However, billions of years of expansion stretched its waves to such an extent that they no longer behave like visible light, but rather like radio waves or microwaves. These waves are incredibly faint and impossible to see with the naked eye, yet we can measure them. By measuring this primordial light from the Big Bang, we detect the CMB, cosmic microwave background. This is the light found at the edge of our observable universe, the sphere that encompasses our entire universe. When we view the CMB as a heat map, the blue and red regions visible to us are not actually blue or red. Instead, these colors represent variations in microwave intensity. The slight fluctuations visible in this heat map correspond to minute temperature differences on the order of a millionth of a degree. This reveals that our universe does not possess a uniform structure. In other words, matter is not distributed with uniform density throughout the cosmos. This aligns with reality, as galaxies in our universe are not evenly spread out, but are instead organized into clusters surrounded by vast, low-density voids. Where the material was slightly denser, gravity pulled more gas toward itself. From these dense areas, galaxy clusters, stars, and ultimately, we were later formed. And where there was less matter, today large empty spaces exist. If our eyes could see microwaves, we would see the night sky not black, but filled with a faint golden glow or fog everywhere. If you turn on an old analog TV and tune it to a blank channel, about 1% of the white noise you see on the screen is echoes of the Big Bang, CMB. But unlike all of this, the most important thing that we learned from the discovery of the cosmic microwave background, CMB, was the age of our universe, or the age of the light that first originated in our universe. From observations of the CMB, we learned that the age of the light at the edge of our observable universe is 13.8 billion years. But here's the problem. We also know that the distance from the center to the edge of our observable universe is 46 billion light-years. So, if the speed of light is constant and no object in the universe can travel faster than the speed of light, then how can light 13.8 billion years old travel 46 billion light-years? To understand this, we will have to go to the beginning of the 20th century. At that time, Albert Einstein was developing a theory called general relativity, which was supposed to explain how the universe works. This theory was to understand the relationship between gravity, time and space, and the speed of light and its behavior. However, there was a problem. Scientists of that era, including Albert Einstein, believed the universe to be static and uniform, meaning its density was the same everywhere. Yet, based on Einstein's own theories regarding gravity, a static universe was theoretically impossible. This was because the attractive force of gravity would pull everything toward one another, eventually causing all matter in the universe to collide and collapse inward. Einstein disliked the idea of an unstable universe, so he introduced a new variable into his equations to rectify this, the cosmological constant. This acted as a form of repulsive force, or anti-gravity, present within the empty space of the universe. It operated in the direction opposite to gravity, balancing out its effects and maintaining the universe's static nature. Interestingly, while Einstein was mistaken about the universe being static, his concept of the cosmological constant turned out to be correct, though he did not realize it at the time. In the mid-20th century, another scientist named Edwin Hubble emerged. Hubble was the first scientist to provide evidence for the existence of galaxies. Before Hubble, scientists believed that every bright point visible in space was merely a star within our own galaxy. He proved that the universe is far vaster than we had imagined and that countless other galaxies, much like our own, exist within it. Hubble's second major discovery was that not only do other galaxies exist, but they are also moving away from one another. Even more intriguing was the finding that the farther a galaxy is from us, the faster it is receding. These discoveries revealed two crucial facts about our universe. It is expanding, and the rate of this expansion is accelerating. This meant that Einstein's theory of a static universe was incorrect. We now know that the universe is not static, but is expanding. However, we still needed to understand the force driving this expansion. This is where Einstein's cosmological constant, or anti-gravity, comes into play. The only necessary adjustment was to recognize that the force of expansion is not merely equal to the force of gravity, but is significantly stronger. In recent years, we have come to know this phenomenon as dark energy, or the energy of empty space. So it is not only expanding the universe, but also pushing all objects away from each other. The further apart objects move, the faster the expansion becomes. This is because more empty space between objects means more dark energy, and more dark energy results in faster expansion. The subject becomes even more fascinating when the speed of the universe's expansion exceeds the speed of light. Einstein established that nothing in the universe can travel faster than the speed of light, a principle that holds true to this day. However, space seems to operate by its own rules, where the rate of expansion can surpass the speed of light. To understand this, imagine that at the onset of the Big Bang, both light and expansion began their journeys simultaneously. While light travels at a constant speed, the rate of expansion continuously accelerates. This explains how light emitted 13.8 billion years ago has traveled through a universe that has expanded to span a distance of 46 billion light years by the time it reaches us. Imagine a highly stretchable rubber band. An ant, representing a photon of light, is at one end and Earth is at the other. When the ant starts moving, let's assume the total length of the rubber band is 10 centimeters. The ant moves toward you at a constant speed. However, as the ant advances, someone stretches the rubber band from behind, making it longer. Consequently, the distance the ant has already covered stretches and increases, and the path it has yet to travel also stretches and lengthens. When that light set out 13.8 billion years ago, its point of origin was much closer to us. However, the distance increased along the way due to the expansion of space. By the time that photon reached our eyes today, the place it started from had moved 46.5 billion light-years away from us due to the universe's expansion. In short, the light traveled at its constant speed, but the road, space, it was traversing was itself stretching and lengthening. That is why we can observe light that is 13.8 billion years old, yet it represents a distance of 46 billion light-years today. To understand this more simply and clearly, let us look back at the Big Bang. We are often taught in school that before the Big Bang, the entire universe was compressed into a region the size of an egg, possessing infinite density. Then, a massive explosion occurred, scattering all the matter outward and forming the universe as we know it today. If we were to reverse this process, theoretically, all celestial bodies should contract back to a single point, a common description of the Big Bang. However, in reality, this is not the case. The universe did not begin at a single point or with a localized explosion. We must keep the observable universe in mind, the bubble containing everything we know to exist. The light emitted during the Big Bang, known as the cosmic microwave background, CMB, is distributed evenly around us, making it appear as though we are at its center. This implies that the Big Bang did not occur at one specific location. Rather, it happened everywhere simultaneously. Consequently, whatever size space was before the Big Bang, it expanded from that state to the scale of the present-day universe in a mere fraction of a second. In that same brief interval, a region of space, the size of a grain of sand, would have expanded to the size of an entire galaxy. If you imagine the pre-Big Bang universe as a bucket filled with sand, then after the Big Bang, every single grain of sand in that bucket would have become equivalent to a galaxy, and even that doesn't come close to the actual scale of the universe's expansion.